In this video, we want to answer the question, what happens when we multiply two binomials by each other? But I want to work up to that question with some simpler examples and then gradually increase the complexity, but still be able to solve based on some patterns that we see. So I want to ask you, if I said to you, what does 3 times 4 equal? You might envision 3 times 4 in a couple of different ways. Maybe you envision 3 times 4 as being something that looks like this, where I have 3 rows of 4 or 4 rows of 3, depending on which way you turn it and look at it. But you might imagine that this is the same as having 3 across here and 4 across here. And you would know that altogether 3 rows of 4 is equal to 12. But what if I said to you, what is 3 plus 1 times 4 plus 1? Well, you would solve inside the brackets, but maybe you also might vision it looking something like this. What if we could say it's equal to 3 times 4, but let's add another row? So let's add the extra row in here, and let's add the extra row in here. And you would see that 3 plus 1 means I end up having 4 rows up here, and 4 plus 1 means I end up having 5 down here. How many total squares are there? Well, there's 20. Okay. Now, a simplified version of this might look something like this. What if you said to yourself, I already know that 3 times 4 is equal to 12, and I already know that 1 times 4 is equal to 4, and that would account for, in the diagram up here, these little 4 blocks right here. And what if you said, I already know that 3 times 1 is 3? Well, that kind of coincides with the blocks in our diagram that are up here. And I know that 1 times 1 is 1. And that would coincide with our block that's right here. And we know that we got 20 in the previous example by adding up all of those individual blocks. So 3 plus 1 times 4 plus 1 has to be equal to 12 plus 4 plus 3 plus 1, or guess what? It also equals 20. Okay? But we wouldn't have to show every single block in order to get the same result. Okay? So what if, instead of working with simple 3's and 4's and constant values, what if we worked with some variables? What if I said to you, I wonder what 2x plus 3 times x plus 1 is equal to? Could we set it up in a similar manner? And the answer is yes, we could. We could put 2x and plus 3 up here, and we could put x and plus 1 here. And in a similar fashion to multiplying each of the rows and columns by each other, we could do the same thing here. So 2x times x would be 2x squared. 3 times x would be 3x. 2x times 1 would be 2x. And 3 times 1 would be 3. And we could put all of these together to say that the answer would be 2x squared plus 2x plus 3x plus 3. And I notice that in this answer I have some like terms here as well. I have a x-type term and another x-type term. And so again, when I add them, I want to make sure that their literal parts are the same, of course, but that I include their signs with their values as well. So this could simplify to be 2x squared plus 5x plus 3. Now, what if I told you that we could get to this answer a whole lot faster than drawing out a grid? Welcome to today's lesson. So, let's introduce you to something called FOIL. FOIL is a cute little acronym, kind of like SOHCAHTOA in some of our previous lessons, to help you remember some mathematical processes. So in the acronym FOIL, FOIL stands for first, O stands for outside, I stands for inside, and L stands for last. So how could FOIL help us multiply 2x plus 3 by 2x plus 1? Well, here's how we could do it. I recognize that this is a binomial times a binomial because there are two different terms inside brackets in both cases, and the brackets are insinuating that these have to multiply by each other. So what if we did a multiplication of the first terms together? Well, 2x times x would be 2x squared, similar to that top left corner of our grid. If we now go to outsides, those are the terms that are furthest away from each other. That's these ones right here. So 2x times 1 would be 2x. And then what if I said to you, hey, let's multiply the insides together? Well, here they are. Positive 3 times x would be positive 3x. And what if we looked at the last terms in each of the binomials, or the 3 times the plus 1? Well, positive 3 times positive 1 would be positive 3. Now, if I simplify this again, I notice that these two terms are like, so they can be collected. 2 things, another 3 things would be 5 things. And remarkably, this looks very, very similar to what you did on the previous page, with what I would suggest is probably a little bit less effort, but the exact same mathematical outcome, just a different way to represent it. Let's look at another example. Let's look at x minus 2 times 3x plus 4. And let's apply our FOIL principles to make this simplified. All right, FOIL stands for first, outside, inside, last. So let's put the first terms multiplied together from each of the polynomials. They're both positive. 1 times 3 is 3, and x times x would be x squared. Next, let's go to the outsides, the ones that are furthest away from each other. They're both positive. 1 times 4 is 4, and x times no other literal part would just be x. Let's now go to the insides. I have negative 2 times positive 3, which is negative 6. The only literal part multiplying them here is an x, so there's an x. And then I just have the last ones to multiply together. Negative 2 times positive 4, which is negative 8. If I look for some like terms in this polynomial, I notice there are 2 of them. There are 4 positive things and 6 negative things. So which one do I have more of? I have more negatives. By how many? Difference between 6 and 4 would be 2. So I can replace this with a negative 2x. And I've successfully multiplied these 2 binomials by each other. Okay. Conversely, if you like the other way, there's nothing wrong with it. You can put an x here, and a negative 2, and a 3x, and a positive 4, and you can multiply them out as well. Okay. This box here gives me 3x squared. This box down here gives me 4x. This box over here gives me negative 6x, and this one gives me negative 8. And look at how that corresponds to what you have in your first inside, outside, last way of doing it. See the color relationships of where each of those terms come from. There you go. Okay, same outcome. There are some benefits to this, though, that we're going to be exploring later in the unit. So while this is not wrong, it's good. this will come in handy for some future things we're going to engage in later in the unit. So if you can start practicing this way, that'd be great. All right, what happens if we increase the complexity a little bit and we introduce a monomial times a binomial times a binomial? Monomial here, binomial, binomial here. What I want you to remember in this scenario so that it doesn't get you into trouble is I want you to do the little Gerberism, do FOIL first. Do FOIL first, do FOIL first, and do uncha uncha dance, whatever it takes for you to remember to do the FOIL piece first. Okay? It's not wrong to go the other way, but in certain scenarios it gets people into trouble. So I'm going to leave that monomial alone, and let's see if we can FOIL this time without the colors. So firsts, 2x times 8x, 2 times 8 is 16, x times x is x squared. Let's go to the outsides. Positive 2 times negative 6 is negative 12, and then x times no other literal will be negative, or just be x, sorry. On the insides, I have negative 4 times positive 8, so negative 32, and I have an x term to go with that. And then in my lasts, I have negative 4 times negative 6, which is positive 24. Now at this point, I think I'm going to clean this up a little bit before we do the monomial distribution. And I notice that negative 12x and negative 32x are like terms. So I have negative 12 of these things and negative 32 of these things. That's a lot of negative things. That's negative 48 of those things, or of those x's. Now I can distribute the monomial. And don't forget, you need to remember to do the sign, the value, so plus or minus, then you got to do the values, then you need to do the bases or their letters, and their exponents. Okay, be mindful of all 4 of those pieces of a term when you multiply. So negative 3 times positive 16 would be negative 48. There's no literal part here, so I'm going to keep the x squared. Negative 3 times negative 48 is going to be a positive value. That's going to be 144 x's. And then negative 3 times positive 24 is going to be a negative. That's going to be 72. And there you go. Simplified through multiplication to a point where all like terms have been collected and we've written the answer as simple as it possibly can be. Okay, one more example. Let's up the ante just a little bit more. And again, let's see if you can start to use FOIL without having to draw, as sometimes we call them, rainbows. See if you can follow the first, outside, inside, last principles when multiplying a binomial times a binomial. Here's one final example. Let's take the monomial 2x and multiply it by the binomial x minus 3, and further multiply it by the binomial x plus 7, minus the binomial 2x minus y and 4x plus 3y. Okay, we have to expand and simplify this. So I notice in this first piece, again, I've got a monomial times a binomial times a binomial, and you are going to do FOIL first. Okay. Over here, I see a binomial times a binomial, but where's the monomial in front of it? Well, this is a tricky scenario. There's no value right here. So when you don't see a value, we're going to put a 1 in there, because then we'll treat it the same way we would if it was a non-1 value. And again, this looks like a monomial times a binomial times a binomial, so we will do FOIL first. All right, let's leave the 2x alone and do first, outside, inside, last. First, outside, inside, last. First, x squared. Outsides, 7x. Insides, negative 3x. Lasts, and again, don't forget about the signs, negative 21. let's leave that -1 alone. And again, let's do firsts, 8x squared. Outsides, 6xy. Insides, -4xy. And lasts, -3y squared. Now, what I like to do before I do all of the monomial distribution is I like to simplify what's in the brackets, just because I'm not going to end up with so many terms and a likelihood for errors. So let's do that. Let's collect like terms within these brackets. So I have x squared. I have +7 things and -3 things. I have more positives by 4. If I look in the next set of brackets, I have 8x squared. I have +6 things and -4 things. I have more positives than negatives by 2. Now I can do the monomial distribution. So this monomial has to get multiplied by all of its monomial friends inside this trinomial. And in a similar fashion, this monomial out front has to get multiplied by all of its monomial friends inside this trinomial. So let's be mindful of the 4 parts of a term as we multiply. So 2 times 1 is 2, and x times x times x is x cubed. +2 times 4 is 8. X times x can be written as x squared. 2 times -21 is -42. Over to green. -1 times 8x squared will be -8x squared. -1 times +2xy will be -2xy. And -1 times -3y squared will become +3y squared. Now, let's skim through and see if we see any terms that are like. I don't see any other x cubed terms, so that one's okay. We'll rewrite it as is. Here's an 8x squared, but here's a -8x squared. So they're present in equal quantities but opposite signs, which means they cancel each other out to become 0. So I have nothing to write there. I then see some other terms. And what I'm going to do is I'm going to write these in decreasing degree of x. So x cubed was the highest degree of x. X squared would have been the next one. There are none. So now I'm going to go x the firsts. So I'm going to choose to write this one first. -2xy. Don't forget the sign as well. If I go to the next two, this one has no literal part at all, so I'm going to write it at the very end. And this one, with its increasing power of y, can be written here. And there you have it. Expansion and simplification of a monomial times a binomial times a binomial and another one after it as well. All right, enjoy your practice and contact me if you have any questions.